Hello, this is tutorial number 14 of the AOU course, Introduction to Linear Algebra, course code M132. This tutorial number 14 is the last tutorial for the course that we will conduct, as this complete our objective for the course. In this tutorial we will start by looking at chapter 5 and specifically section 5.1 of this chapter. And section 5.1 talks about eigenvalues and eigenvectors of a matrix. In other words, we will learn how to find eigenvalues and eigenvectors and the meaning of these two terms. As usual, we'll start off by a definition, and the definition for eigenvalues and eigenvectors. If A is an n by n matrix, therefore A is a square matrix, a number lambda is called an eigenvalue of A if there exists a non-zero vector x such that A times x, the matrix A times x, is equal to lambda times x. Every vector x satisfying the above equation is called an eigenvector corresponding to the eigenvalue. Therefore, so from this equation here we have ax equal to lambda x. Therefore, if we move all these to one side, we have lambda x minus ax equal to 0. We can take x as a factor, therefore lambda times I minus a times x equal to 0. This is valid provided x is non-zero. So then let's further expand on these ideas by looking at some notes related to this subject. The number lambda is an eigenvalue of an n by n matrix A if and only if the determinant of lambda I minus a is equal to 0. And lambda I minus a equal to 0 is called the characteristic equation. The eigenvectors x associated with the eigenvalue lambda is a solution of the homogeneous linear system lambda in minus a times x equal to 0. So then this slide is very important, as it defines how we calculate the eigenvalue and how we find the corresponding eigenvector. Therefore, to recap, in order to calculate the eigenvalues, we find the determinant of this expression and we set it equal to 0. This equation is called the characteristic equation, and solving it by setting it equal to 0 will give us the values of the eigenvalues. Then, to determine the eigenvectors, we solve this homogeneous system here to find the eigenvectors. Let's work on some examples as we see in the next slide. If A is a 2 by 2 matrix as seen here, where A is equal to 1, 2, 0, minus 1, the question is to find the eigenvalues and the corresponding eigenvectors of A. Then we apply the definitions that we've seen in the previous slide. Mainly, we need to find lambda I minus a as we see here. Then we find the determinant of this matrix here, 2 by 2 matrix, and we set it equal to 0. If we do so, we have a, b, c, d, and the determinant is ad minus bc. So then the determinant is lambda minus 1 times lambda plus 1 equal to 0. This characteristic equation has for solution lambda equal to 1 and lambda equal to minus 1. We'll set the first one as being lambda 1 and the second solution as being lambda minus 1, lambda 2 equal to minus 1. Sorry. Now we move to calculate the corresponding eigenvectors for A. And for lambda 1 equal to 1, we substitute the values in the equation that we talked about in the second slide, which is the homogeneous equation. Lambda 1 times I minus a times x equal to 0. We substitute the values. Solving the system here is the same as having this augmented matrix. After doing the corresponding elimination, row reduction, we obtain the row reduced matrix here, augmented matrix here, 0 1 0 0 0 0. It is obvious here that x2 is equal to 0, therefore x1 is equal to r, where r belongs to the set of real numbers. Therefore x is equal to r0, and if we take r as a factor, therefore x is equal to r times 1 0. So then x1, which is the eigenvector, is equal to 1 0, and this eigenvector corresponds to lambda 1 equal to 1. Now for lambda 2 equal to minus 1, we do the same thing. We substitute the value of minus 1 here. We obtain the matrix minus 2 0 0 times the eigenvector that we need to find, x1 x2 equal to 0. We have to solve this homogeneous equation here. Again, we do the row reduction to obtain this row reduced version of the augmented matrix. It is clear here that x2 is equal to s, where s belongs to r, set of real numbers, and x1 is equal to minus s. So then x is equal to minus s and s. If we take s as a factor, therefore x is equal to s times minus 1 1. So then x2, which is equal to vector minus 1 1, is the eigenvector that is associated with lambda 2 equal to minus 1. Let's look at another example, example 2. Find the eigenvalues and eigenvectors of the 2 by 2 matrix here, A equal to 2 minus 12, 1 minus 5. First we have to find the characteristic equation as we've done before. We need to find the determinant of lambda I minus A, and this is it here. So then if we apply the find the determinant of this 2 by 2 matrix, we have AD minus BC. Therefore it becomes lambda plus 1 times lambda plus 2 equal to 0. So then lambda, the solution to this characteristic equation is lambda equal to minus 1 and minus 2. So that lambda 1 is equal to minus 1 and lambda 2 is equal to minus 2. Now we move to finding the corresponding eigenvectors. As we've done before in the previous example, we start off by looking at lambda equal to minus 1. We substitute this in the homogeneous equation as we have seen in a second slide of this tutorial, where we have a lambda I minus a times x equal to 0. We set lambda here to equal to minus 1, so then we obtain the following homogeneous system, where x1 and x2 are the variables, and x1 and x2 are the proposed values for the eigenvector that we need to find. So then we are left with this augmented matrix here. If we apply the row reduction, the augmented matrix that we obtain is 1 minus 4 0 0 0 and 0. Therefore x2 is equal to t, where t belongs to r, and x1 is equal to 4. So then x, the eigenvector, is equal to 4t and t, which is equal to, if we take the t as a factor, t times 4 1. So then x2 is equal to 4 1 is the eigenvector associated with lambda 2 equal to minus 1. Now to find the second eigenvector that is associated with lambda equal to minus 2, we have again, we substitute the value of lambda in this homogeneous equation here to obtain the following matrix: minus 4 12, minus 1 3, and this is x1 x2, which corresponds to the proposed values of x, the vector x, equal to 0. Then the augmented matrix becomes like this. We apply row reduction to obtain the following augmented matrix. Here again, x2 is equal to s, where s belongs to r, the set of real numbers, and x1 is equal to 3s. Therefore x is equal to 3s and s. Taking s as a factor, this becomes s times 3 1. So then x2, the second eigenvector associated with lambda 2 equal to minus 2 is 3, 1. Finally, as a conclusion for what we have seen so far, we notice the following. Eigenvalues are used to find eigenvectors. It is clear, this is clear from our previous two examples. The sum of the eigenvalues is called the trace of the matrix. The product of the eigenvalues is the determinant of the matrix. A square matrix A is singular if and only if lambda is equal to 0 is an eigenvalue of A. An eigenvector of an n by n matrix A is a vector such that Ax equal to lambda x, where x is the eigenvector. An eigenvector is a direction for a matrix X. This ends our tutorial for section 5.1 of the course. Thank you very much and good luck.